Hello and welcome to the Free Education Project. I'm Dr. Mitchel Goodkin. As a nationally board certified science teacher with over 20 years of educational experience, I've realized there are many children all over the world who could benefit from all the years of lessons I've created. I'm recording them for free use by anyone, regardless of ethnicity, region, religion, or politics. I'm committed to the belief that as adults, it is our responsibility to prepare children to improve the world so they might grow and lead happy, healthy lives. Please, if you have a pencil and paper, take notes. If you live in an area where supplies are scarce, just pay attention. Let's learn. Hi, everyone. When we last met, we spoke about density, and density, as we said, was the ability to calculate something's mass or weight in relationship to its size. So sometimes you think something that's really big is going to weigh a lot, and it doesn't, or something really small, you pick it up and it's very heavy. So that's all density. So we've learned to calculate density, we've learned to calculate volume, we've learned to measure. So now we're going to look at something called buoyancy. So let's get right into the PowerPoint for today. So buoyancy, and that's to float or sink. That is the question. So buoyancy relates to density, and everything in the universe has a certain density. A medium is an object that surrounds other objects. So water is the medium for fish. So fish live in water. Air is the medium for people. We live in air. The density of an object is less than the density of the medium, then the object will float. And this is called positive buoyancy. It floats. If the density of an object is greater than the density of the medium, then the object will sink. And we call that negative buoyancy. So positive buoyancy, it floats. Negative buoyancy, it sinks. The density of the object is the same as the density of the medium, then the object will neither sink nor float, it will just hover. And that's called neutral buoyancy. So neutral buoyancy is when the density of the object is the same as the density of the medium, and they match each other. So how much something sinks or floats depends upon the relationship between the two densities. Find out how much an object will float, the density of the object, and divide that by the density of the medium, then multiply by 100. Your answer is what percentage of the object will sink below the surface line. Let's imagine an example of a red ball floating in a glass of green liquid. So that would be density of the ball divided by density of the liquid times 100, and that would give us our percent. So let's take a look here. So if the density of the liquid is 4 grams per cubic centimeter, and the density of the ball is 2 grams per cubic centimeter, and I'm rounding off to the nearest whole gram. So we do d ball over d liquid times 100. So that would be 2 grams per cubic centimeter over 4 grams per cubic centimeter. So 2 over 4 is 0.5 times 100 is 50%. So if you look at the ball is exactly halfway sunken. It doesn't go all the way under, it only goes halfway. That's 50%. So watch closely. Even if this ball is 50% below the surface line, right? So that's because the density was 0.5 times 100. Even if we were to push the ball below the surface, it will always come back to the 50% mark. So even if we push it below, it still comes back to that point, to 50%. And that has to do with the relationship between the density of the ball and the density of the medium, or the liquid in this case. So where would the ball be if the density of the ball was 12 grams per cubic centimeter and the density of the liquid was 48? Well, we use the same formula, density of ball divided by density of liquid times 100. So that would be 12 grams per cubic centimeter over 48 grams per cubic centimeter, which would give us 0.25 times 100 is 25%. So let's see what that would look like. So 25% of that ball would go below the surface of the liquid. So depending upon the density, it could look like any of these. 10% where only a little bit is below the liquid, 20%, 30%, 40%, 50% where half of it's below the liquid, 60%, 70%, 80%, 90% where almost all of it is below the liquid. And that has to do with the density, the relationship of the density between the ball and the liquid. So what would happen if the density of the ball equals the density of the liquid? Well, let's see. Here's the liquid. Here's another liquid. If the density of the ball equals the density of the liquid, and I put it right in that spot, it will stay in that spot. It won't go up. It won't go down. It'll stay exactly there. If I put it in this spot, it will stay exactly in that spot. It won't go up. It won't go down. It'll stay exactly there. It's neutral. The ball will hover in the liquid exactly where you put it. What if the density of the ball is greater than the density of the liquid? Well, let's see what that looks like. It will sink to the bottom. Here again, it will sink to the bottom. Notice that this one sank slowly. And this one sank fast. Well, reason the first one sank slowly is because the density of that ball is a little bit more than the density of the liquid. It'll still sink, it'll still go to the bottom, but it'll take it a little bit longer to do it. And on the other one where it sank very fast, that's because the density of the ball was a lot greater than the density of the liquid. So it just went straight down fast. So here we're going to look at that. If the density is only a little bit greater, then it will sink slowly. So let's pretend the density of the ball is 4 and the density of the liquid is 3.9. I should say 4.0 there, but I didn't. So let's say it's 4.0 and the density of the liquid is 3.9. Well, it's only a little bit. It's a 1/10 of a gram per cubic centimeter greater than the liquid, which means it will sink. It's going to sink very slowly. And it'll go till it hits the bottom. So if the density is a lot greater, it will sink fast. So let's pretend the density of the ball is 49 grams per cubic centimeter, and the density of the liquid is 2 grams per cubic centimeter. So that's a lot greater. That's more than 24 times greater, almost 25 times greater. Let's see what it looks like. It goes straight down immediately. And that's because there's such a difference between the density of the two objects. So here's some good news, though. If the liquid in the cup is water, then it changes everything because the density of water is 1 gram per cubic centimeter. And you need to memorize this. This is really important. Density of water is 1 gram per cubic centimeter. And that's pure water. Seawater is differently and pool water is differently. That's just pure water. So if it's the density of water is 1, that makes life a lot easier. If the density of water is 1, it would make the denominator 1, the bottom part of the fraction. And any number divided by 1 is the original number. Therefore, we can just take the density of the object and multiply it by 100%. And remember, this only works for water. So let's imagine we have the red ball floating in a glass of water. The density of ball over density of water. Before I had density of ball over density of liquid. In this case, the liquid is water times 100. Now remember, water is a density of 1. So the density of water is 1. The density of the ball is 0.5 grams per cubic centimeter. So if we put 0.5 grams per cubic centimeter over 1, it times 100 is 50%. Or we could just say 0.5 grams per cubic centimeter times 100% is 50%, because remember, it's 1. Okay, these are some homework problems I used to give my students. Okay, So that is buoyancy. Let me shut off the stop sharing. Okay, so that is buoyancy, and that's really exciting, and it gives us a practical application for calculating density. Next time I see you, we're going to expand on this even further. And again, thank you for joining me. I hope you go back and watch this as often as you want. If you want to take notes, take notes. If you don't have the ability to take notes, just pay attention and watch it over and over and over again. Again, we are here to help you, and we are here to make sure that children everywhere can learn. So have a great day, and I will see you soon. Bye-bye. Thank you for your attention. That concludes this lesson from the Free Learning Project. Thank you for sharing this learning experience with me. Sometimes it's unclear what the practical day-to-day use of a lesson might be. However, much of the learning process is really a way of disciplining and training our minds. It teaches us how to learn, and that prepares us for whatever lesson might come tomorrow. We would like to thank the Hocus Pocus Children's FUN-dation Incorporated for sponsoring this programming. Put your whole hearts in and turn some lives around. Thank you.